Welcome back, everyone, to the Deep Dive. Today we're going to try to unlock the mysteries of these things called quantum gates.
Oh, yeah.
Which sound kind of intimidating, right?
Yeah.
But they're basically the instructions, the tiny little instructions that power quantum computers. They're kind of like the logic gates in our everyday computers.
Yeah, that's a great analogy.
But with a quantum twist?
Yeah, quantum gates are the building blocks of quantum algorithms.
Oh.
And algorithms are basically just sets of instructions that tell the quantum computer what to do.
So they're like the individual commands in a programming language.
Exactly.
But for the quantum world.
Yeah, and instead of manipulating bits like in our classical computers, which can be either a 0 or a 1,
Right.
Quantum gates work with qubits.
Okay, so qubits are like the quantum version of bits.
Exactly.
But what makes them so special?
Well, imagine a qubit like a spinning coin before it settles. So it's not heads, it's not tails.
Right.
It's both possibilities existing simultaneously. And this both at once state is called superposition. And that's one of the things that makes quantum computing so powerful.
So unlike a bit, which is stuck being either a 0 or a 1, a qubit can be in this fuzzy in-between state.
Yes.
That's pretty wild.
It is wild.
So these quantum gates are what allows us to control and manipulate these qubits.
Yeah.
Including putting them into a superposition.
Exactly.
Okay, let's try to compare these quantum gates to the classical computer gates that we're a little bit more familiar with.
Okay.
So just to get our bearings.
Sure. Think about a simple NOT gate.
Okay.
Which is like flipping a light switch.
Okay, so if the light is on in,
yeah,
we can think of that as a 1. Flipping the switch turns it off or 0.
Exactly.
And vice versa.
Right. The NOT gate flips the state of a bit.
Okay.
Now, in the quantum world, we have a similar gate called the X gate.
Okay.
It does the same thing.
Okay.
To a qubit flips its state. If the qubit is in state 0, the X gate changes it to state 1.
Okay.
And if it's in state 1, it changes it to state 0.
Okay, so that's pretty straightforward.
Yeah.
But I thought you said that quantum gates can do more than just flip states.
Actually, remember superposition.
Right.
Quantum gates can also be used to put qubits into that mind-bending state where they're both 0 and 1 at the same time.
Right, the spinning coin analogy.
Yes.
So how do they do that?
Well, one of the key players here is the Hadamard gate.
The Hadamard gate?
Yes. Think of it as a gate that takes a qubit. And instead of just flipping it, puts it into a 50-50 superposition, just like our spinning coin.
Okay.
After going through the Hadamard gate, the qubit has an equal chance of being measured as a 0 or a 1.
So the Hadamard gate is what creates this, maybe it's heads, maybe it's tails state?
Precisely.
For the qubit.
Yes.
Okay, so we've got the X gate, which is the quantum version of the NOT gate. We've got the Hadamard gate, which creates superposition.
Yeah.
What other types of quantum gates are there?
There are many, but let's focus on a couple more single-qubit gates that are really important.
Single-qubit gates meaning that they only act on
a single qubit at a time.
At a time.
Yes.
Got it.
One is the Z gate.
Okay.
Instead of flipping the qubit, it does something a bit more subtle.
Okay.
It affects the phase of the qubit.
What does that even mean?
Imagine you have a wave, like a water wave. The phase of the wave tells you where you are in the up and down cycle of the wave.
Okay, so the peak of the wave versus the trough.
Exactly. Qubits, believe it or not, can also be thought of as having these wave-like properties.
Okay.
The Z gate shifts the phase of that qubit's wave.
Interesting. But why is the phase important?
It affects how the qubit interacts with other qubits.
Oh.
You can think of it like two waves interacting. If their peaks and troughs line up, they reinforce each other.
Okay.
If they're out of phase, they can cancel each other out.
Gotcha.
So the Z gate allows us to kind of fine-tune these interactions.
Okay. I think I'm starting to get it.
Oh.
So we've got the X gate, the Hadamard gate, and the Z gate all acting on individual qubits.
Yes.
What about entangling two qubits together?
Okay.
How do quantum gates do that?
That's where the CNOT gate comes in.
Okay.
And that's where things get really, really interesting.
I'm ready.
So to understand the CNOT gate, let's start with a very mind-boggling concept called entanglement.
Okay.
So imagine two coins that are magically linked so that no matter how you flip them, they always land on the same side, even if you flip them miles apart.
That sounds impossible.
It does, right? But that's entanglement.
Oh, wow.
This spooky connection between two qubits where their fates are intertwined no matter how far apart they are.
Wow.
And the CNOT gate is the tool that we use to create this entanglement.
In a quantum computer?
Yes.
Okay, I'm hooked. Tell me more about the CNOT gate.
So the CNOT gate has two input qubits, a control qubit and a target qubit.
Okay.
If the control qubit is a 1, the CNOT gate flips the state of the target qubit. If the control qubit is a 0, it leaves the target qubit alone.
Okay.
It's kind of like the control qubit is saying, hey, target qubit, if I'm a 1, you have to flip.
So how does that create entanglement?
So let's say we first put the control qubit into a superposition.
Okay.
Using that Hadamard gate.
Right.
So remember, that means it's in this maybe 0, maybe 1 state. Now we apply the CNOT gate.
Okay.
Because the control qubit is in superposition.
Right.
It's kind of like it's both 0 and 1 at the same time.
Right.
So it's both telling the target qubit to flip and not to flip simultaneously.
Whoa, that's getting a little trippy.
It is, but the result is that the two qubits become entangled. Their states are linked. Even if we separate them.
Okay.
Measuring one qubit instantly tells us the state of the other one, no matter how far apart they are.
So if I measure the control qubit and find that it's a 1, I instantly know that the target qubit has been flipped.
Exactly. It's like they're connected by an invisible thread.
It's amazing. But I have to ask, like, if we're manipulating these qubits with quantum gates,
right,
and they're so sensitive,
yeah,
what happens if there's, like, interference or errors?
Right.
Does that mess things up?
It absolutely can. And that brings us to the challenge of noise in quantum computing.
Okay, let's dive into that.
Okay. Yeah.
Noise is a big problem.
Yeah, it is.
In quantum computing.
Huge problem. Yeah. Yeah, it's like static on a radio signal. But for qubits, it can come from things like temperature changes, electromagnetic interference, or even just the qubit losing energy over time.
So if a qubit gets hit with noise, does that mean, like, game over for our calculation?
Pretty much, yeah. Noise can cause a qubit to accidentally flip its state or lose its superposition. And that leads to errors in the computation.
So that sounds like a major roadblock for building, like, reliable quantum computers.
It is. It's one of the biggest challenges.
Yeah.
Researchers are working really hard to find ways to reduce noise and make qubits more robust.
Right.
It's like trying to build a super sensitive instrument in a noisy workshop. You need to find ways to, like, isolate it from all the disturbances.
Right. So we've talked about single qubit gates.
Yes.
Like the X to Z and the Hadamard gates.
Yes.
And we've seen how the CNOT gate can entangle two qubits together.
Yes.
But I'm guessing there's a lot more to it than just these few gates, right?
But you're absolutely right. Those gates are just the beginning. We can combine them in all sorts of ways to create more complex operations.
Kind of like building with Legos.
Exactly.
You start with the basic blocks, and then you can snap them together to create bigger and more intricate structures.
Exactly. In quantum computing, we string together these basic gates, both the single qubit gates and two qubit gates like the CNOT, to create what are called quantum circuits.
Quantum circuits.
Yes, and these circuits are like the blueprints for quantum algorithms.
Okay.
The sets of instructions that tell a quantum computer what to do.
So a quantum circuit is like a recipe for a quantum computation.
Yes.
And each gate is like an ingredient or an instruction in that recipe.
That's a great way to think about it. And just like any good recipe, the order in which we apply these gates really matters.
So the way we arrange these gates in a quantum circuit determines what kind of calculation the quantum computer will perform.
Precisely. We can create circuits that perform all sorts of amazing calculations. Things that would be impossible for classical computers to do in any reasonable amount of time.
Wow, it's like having this whole new set of tools that allows us to solve problems in a completely different way.
Yeah.
But how do we know which gates to use and how to arrange them?
That's where quantum algorithms come in.
Okay.
Researchers are developing very clever algorithms that are designed to take advantage of the unique properties of quantum mechanics.
So these algorithms tell us how to build the quantum circuits to solve specific problems.
Exactly. It's a whole new field of computer science.
So we have these basic quantum gates, and we can combine them into quantum circuits to carry out complex computation. Is there a set of gates that's considered like the most fundamental, like the essential building blocks for everything else?
Yes, that's a great question. There's a concept called a universal gate set.
Universal gate set.
And it's a set of gates that's powerful enough to approximate any quantum operation you can imagine.
Wait, so any quantum computation, no matter how complex, can be broken down into a sequence of these universal gates?
Exactly. It's kind of like having a master set of tools that can be used to build anything.
Wow, that's pretty powerful.
It is.
So what gates are in this universal set?
There are actually different combinations of gates that can form a universal set.
So there's no one right set?
Right. One commonly used universal gate set includes the Hadamard gate. the phase gate,
Okay.
which is similar to the Z gate but can create more general phase shifts, the CNOT gate, and a few others.
Okay.
With just these few gates, we can build incredibly complex quantum algorithms.
That's fascinating. So we've got the software side of things figured out.
Right.
We know how to create algorithms and circuits using these universal gates.
Yeah.
But what about the hardware?
Right.
How do we actually build a machine that can execute these quantum operations?
That's where things get really, really tricky.
Okay.
We need a physical system that can embody these quantum properties and allow us to manipulate qubits very precisely. And there are a number of different approaches that are being explored, each with their own pros and cons.
So it's not as simple as just like building a regular computer chip, but with qubits instead of bits?
No, it's much more challenging. Qubits are incredibly delicate and sensitive to their environment.
Okay.
It's like trying to balance a feather on your fingertip while standing on a roller coaster.
That sounds difficult.
It is one promising approach uses trapped ions.
Trapped ions?
Which are basically single atoms that are electrically charged and held in place by electromagnetic fields.
So we were literally trapping atoms and using them as qubits.
Exactly. And we can manipulate their quantum states using lasers or microwaves.
Wow.
Another popular approach is using superconducting circuits.
Okay.
These are tiny electrical circuits that are cooled down to extremely low temperatures, where they exhibit quantum behavior.
Why do they need to be so cold?
At those ultra-low temperatures, the electrical resistance in these circuits disappears completely, and they become superconductors. And this allows us to create and control qubits using electrical pulses.
So it's like two completely different ways of building a quantum computer.
Right.
One using trapped atoms and lasers, the other using super-chilled circuits and electricity.
That's right. And there are other approaches being explored as well, like photonic systems that use particles of light as qubits.
It's incredible how much research is going into building these machines.
It is.
But it sounds like there are still a lot of challenges to overcome.
Absolutely. Building a large-scale, fault-tolerant quantum computer is one of the grand challenges of our time.
But the potential is there, right? If we can crack this, it could lead to some truly revolutionary advancements.
It has the potential to transform fields like medicine materials, science, artificial intelligence, and many more.
Well, it's a great place to leave our listeners for now, pondering those possibilities. Okay, so we're back. And, you know, I got to say, I am just so captivated by this whole world of quantum gates.
Yeah.
It's like we've been peeking behind the curtain of, like, reality.
Yeah.
And seeing how the universe computes, like, at its most fundamental level. You know?
It's pretty mind-blowing to think about.
One of the things I'm struggling with, though, is like how different this all is from our everyday experience. Like entanglement, for example. It still feels like something out of science fiction to me.
It is very strange.
Yeah.
For sure.
How can two particles be so, like, intimately connected, even across vast distances?
It's one of the deepest mysteries in quantum mechanics.
Right.
It really challenges our classical intuitions about how the world works. But the experiments have been done over and over again. And entanglement is real.
So what's the current thinking on, like, how it works?
Right.
Is there any way to explain it without getting too deep into the weeds of quantum theory?
Well, one way to think about it is that entangled particles, they share a common history.
Okay.
So they were once part of the same system. And that connection kind of persists, even when they're separated.
So it's like they have this shared memory.
In a way, yes, but it's not a memory in the classical sense. It's more like their fates are intertwined. Whatever happens to one particle instantly affects the other, no matter how far apart they are.
But you mentioned earlier that we can't use entanglement to send information faster than light.
That's right.
So how is that possible?
Entanglement doesn't allow us to communicate faster than light.
Okay.
Think of it like this. Imagine you have two gloves, one left and one right. You put one glove in a box and ship it to your friend on the other side of the world. When you open your box and you see the left glove, you instantly know your friend has the right glove.
But you haven't actually sent any information to your friend faster than light. The information about which glove they have was determined like the moment you separated the gloves.
Exactly. And it's the same with entangled particles. Their states are correlated, but no information is actually traveling between them faster than light.
So entanglement is more like sharing a secret code than like sending a message.
Exactly.
I like that.
That's a great analogy.
Yeah, so how do these quantum gates actually create entanglement?
Remember the CNOT gate?
Yes.
It's a 2-qubit gate that can be used to create entanglement. If we put the control qubit in a superposition and then apply the CNOT gate, it entangles the control and target qubits.
Right, because the control qubit is in this maybe 0, maybe 1 state. So it's both flipping and not flipping the target qubit at the same time.
Exactly.
Mind-bending, but I'm starting to see how it works.
Good. And it's this entanglement that gives quantum computers their edge.
Okay.
It allows them to explore many possibilities simultaneously, which can speed up certain calculations tremendously.
So even though entanglement itself doesn't allow for faster-than-light communication, it's still the key ingredient in what makes quantum computers so powerful.
Absolutely. It's what allows them to perform computations that would be impossible for classical computers to do in any reasonable amount of time.
Well, I have to say this deep dive into quantum gates has been an incredible journey.
Yeah, me too.
You know, we've gone from simple logic gates to mind-boggling concepts like superposition and entanglement. And we've seen how these quantum gates are like the building blocks of a whole new kind of computing.
It's amazing.
One that really has the potential to revolutionize our world.
For sure.
So thanks for joining us today on this deep dive into the quantum realm.
You're welcome.
And until next time, keep exploring and keep asking questions.